In this video, we're going to be talking about the first derivative test. This is from section 4.5 in the OpenStax Calculus 1 book. Before we begin talking about the first derivative test, let's remind ourselves what critical values are that we studied in section 4.4. Critical values come from two places. A critical value or a critical point on a graph occur in possibly two places. One, where the first derivative is set equal to 0. These are the x-intercepts on the graph of the first derivative. That does not mean that they're relative extrema values. It does mean that it's a possible place to find a relative extrema. The other place that you can find a critical point is when the first derivative of the function does not exist, and the second part is crucial. While the first derivative does not exist, the function does exist at that point. This is very important to remember. You cannot have a critical point if the function does not exist at that point. Critical points are always points in the domain of the original function f. They're points in the domain where either the first derivative crosses the x-axis, it's an x-intercept of the derivative, or the first derivative does not exist, but the function does. If we look at the graph here in section 4.31, we see that we have several critical points occurring at x equal a, x equal b, x equals c, and x equal d. Let's remind ourselves of what these are like. At the point x equal a, we see that the original function f has a cusp. This cusp corresponds to a point where the first derivative does not exist, but the function is defined there. That is not a hole in the graph, nor is it a vertical asymptote. So we can have a corner or a cusp or a point where the tangent line goes vertical. All three of those would correspond to places where the first derivative does not exist, but the function does. These would look like the following three cases: a corner, as in the absolute value function, a cusp, like the one we see above, or a graph where the tangent line goes vertical at one point, but the function is definitely defined there. That is what we see at x equal a. Notice that that point, while the first derivative does not exist, it does count as a relative maximum. It is higher than all the y values around it. Now let's take a look at the next point. When x equal b, we can see that the original function f has a low spot in the graph. This is a place where the tangent line becomes horizontal. This corresponds to a critical value where the first derivative is 0. In the graph of the first derivative, we would have an x-intercept at that point. That means that we have a relative extrema here, and in fact, ours is a relative minimum. It does not count as the absolute minimum of the graph because you can see that on the far right, the graph continues to go down forever. In fact, that implies that the graph does not have an absolute minimum at all. The next value that we see that has a critical point is at c. C is an interesting point because the first derivative is 0 here, but it is not a relative maximum or a relative minimum. This is what I tend to call a saddle point. If you ever do much hiking in the mountains here in Colorado, you know that sometimes you come up to what is called a false peak, meaning it appears that you're approaching the top of the mountain, but when you come over the rise, you realize that the ground simply flattened out for an instant and then goes up again. You have not reached the top of the mountain, but you are not at the bottom of a valley either. You're at what's known as a saddle point. That means that it is neither a maximum nor a minimum, but there is an instant where the slope of the tangent line does go to 0. It is a critical point, but it is not a relative extrema. The fourth place in this graph where we have a critical point is at x equal d. At x equal d, we can see that the graph has a relative maximum. In fact, we must have an absolute maximum here occurring at x equal d, and the relative maximum value is the y value, f of d. Notice that it also has a tangent line with slope of 0. The critical points do not guarantee that you will find a relative extrema. They simply give the places where it could occur. Now let's analyze the sign of the first derivative and see how it is related to where the relative extrema occur. Notice that the x-axis has been divided into 1, 2, 3, 4, 5 regions between the dotted orange lines. These correspond to the intervals over which the function is defined, split up according to the critical points. When you split the domain of the function into its critical point intervals, you can analyze the sign of the first derivative between them. The first derivative cannot change sign from positive to negative if it is continuous without crossing the x-axis. That accounts for the first set where the first derivative is 0. If it is not continuous, it is possible for it to cross and become positive to negative or negative to positive if it is a place where the first derivative does not exist. This accounts for the second set of possible critical points. By analyzing the sign of the first derivative, positive or negative, we can predict whether the graph is increasing or decreasing over that interval. A graph will not change its increasing or decreasing behavior except at critical points, but it is not required to change at the critical points. Let's look at the first interval on the far left. This is the interval from negative infinity to the first critical point at A. We can see that over this region, the graph is generally going uphill. Because it is uphill, that means it is increasing, and the first derivative will be positive. On the right side of A, on the next interval between A and the next critical point B, we can see that the graph is generally downhill, which means that the first derivative is negative. The slope of the tangent line is downhill. Notice that this means that the graph is generally going down. If the graph was going up and now it's going down, we must have a relative maximum at the point in between. That means that we have a relative maximum here at the point x equal a, and the relative maximum value is f of a. This corresponds to the critical point where the first derivative does not exist because it is a cusp, but the function does. Let's look at the next interval between B and C, the next critical point. Again, the graph is generally uphill, which means that the first derivative is positive. That means the graph is going up. Notice that we had been going down, and then at B we start going up. This means that we must have a relative minimum here at the point B, f of B. Now let's take a look at the next point. Between C and D, what happens? Between the two critical values C and D, the graph is generally uphill, which means the first derivative is again positive. Now, at the saddle point, that means that I was going uphill, flattened for an instant, and continued uphill. Because the first derivative did not change sign there, I do not have a relative extrema. It is, in fact, a saddle point on the graph. What about over the last interval, which is from D to positive infinity? From D to infinity, the graph is generally downhill, which means that my first derivative values must all be negative. downhill sloping tangent lines. This means that I was going uphill to the left of D, and now I'm downhill to the right of D, which again means I have a relative maximum at D, f of D. To find where your absolute maxima and minima are, you must look at the graph as a whole. In other words, by analyzing the sign of the first derivative and whether it was increasing or decreasing, we were able to figure out which of the critical points had to correspond not only to the extrema, but to which extrema it had to be, whether it had to be a relative maximum or a relative minimum. We are also able to identify the point where it did not change from uphill to downhill and continued uphill and became a saddle point. This is the first derivative test. Let's look to see how the first derivative test is written mathematically. This is the statement of the first derivative test. Notice that it does have a condition. The condition is that the function is continuous over the interval I and that I contains a critical point C. This corresponds to having a continuous function over its domain and having critical points within that domain. Now, provided that the function is differentiable over the interval, except maybe at C, where it could have a corner, a cusp, or a vertical tangent line, we can draw the following conclusions. If the first derivative changes sign from positive, meaning going uphill, to the left of C, to negative, meaning going downhill to the right of C, then we must have a local maximum at x equals C, and the y value, f of C, is the local maximum. If the first derivative changes sign from negative, meaning going downhill to the left of C, to uphill or positive to the right of C, then we must have a local minimum at x equals C, and f of C is the value of that local minimum. On the other hand, what about a saddle point? What if we have the same sign both to the left and to the right of C? Then it is not a local maximum and it is not a local minimum. It corresponds to a saddle point on the graph. How can we use this to graph functions? Let's look at the next box, which will give us our strategy for graphing. In the gold box, it explains how to use the first derivative test to predict where you have relative extrema and to know where the graph is increasing and where it is decreasing. Step 1 means you need to find all the critical points of the function. Use the critical points to divide the domain of the function into smaller intervals. Once you have divided the domain of the function into smaller intervals with the critical points as the endpoints, then analyze the sign of the first derivative in each of those subintervals. If the first derivative is positive, it is increasing. If the first derivative is negative over that interval, it is decreasing. Then you can use this information to determine whether it has a local maximum at the critical point, a local minimum, or neither. Let's take a look at an example. Your book and I do these slightly differently. Your book uses a table and I use an expanded number line to organize the information. You can use either method. In this particular picture, you can see an original function, x cubed minus 3x squared minus 9x minus 1. We're going to take this and analyze it using the first derivative test. First step is to find the derivative. The derivative of this function, hang on just a moment. Let's find the derivative. To find the derivative, I simply apply the rules I've already learned, in this case, mostly the power rule. This gives me 3x squared minus 6x minus 9. I can factor out the common 3, leaving the quadratic x squared minus 2x minus 3, which can be further factored into 3 times the binomial factors x minus 3 and x plus 1. Notice that the original function, the cubic, is a polynomial which is defined on all real numbers, continuous everywhere, and differentiable everywhere. The first derivative is in fact a quadratic, so it is also a polynomial defined everywhere and continuous everywhere and differentiable everywhere. You will see in this table from the textbook that they have already written the first derivative at the top in the third column. We need to find the critical points of the first derivative to apply the first derivative test. So now I will find the critical points of the first derivative. I look in 2 places, the first derivative equal to 0 and the second one, the first derivative does not exist, but the function f of x does. Now, since the first derivative is a polynomial, it exists everywhere. So there are none coming from the second case. The first case, however, I do have solutions. The first case, I know that the monomial factor 3 is never 0. It doesn't provide a solution, but it is a factor of the first derivative. The second factor is the binomial x minus 3, and when I set it equal to 0, I get the solution x equals 3. The third factor is the binomial x plus 1, and when I set it equal to 0, I get the solution x equals negative 1. This gives me 2 critical values, negative 1 and 3. I will take the information and create a number line for each of the factors that occur in the original first derivative. This includes the monomial factor 3, even though it did not contribute a critical point to my list. Here are the 3 factors. 3 by itself, x minus 3, the binomial factor, and x plus 1, the binomial factor. Together, these provide the combination of f prime. You can either write combo or you can write f prime to indicate the last one. We're going to write 4 number lines, 1 for each of the 3 factors and 1 for the first derivative or the combination. This is different than the way that the book organizes the information in the table. But again, you're allowed to choose the method that makes the most sense to you and that you prefer to use. They are equivalent and they will give the same results. Now we look at our critical values. We have a critical value of negative 1 and a critical value of 3. Negative 1 on the number line is to the left, so I draw a long vertical bar and I label it negative 1. Then I draw a long vertical bar for the other critical point and I label it 3. Now I need to find test points. You will notice that what I've produced is sort of like a chart similar to the table. I have divided up the number line into regions from negative infinity to negative 1, just as the table did. Between negative 1 and 3, again like the table, and from 3 to infinity, also like the table. Now I need to choose some test points. For test points, I'm going to choose the values. Well, let's see. To the left of negative 1 are infinitely many numbers, but the easiest to plug in would be negative 2. I'll write it and circle it so I know which one to use. Between negative 1 and 3, there are lots of values, but 0 or 1 would probably make the most sense. So I'm going to choose 0 for the center section and circle it. To the right of 3, there are again infinitely many numbers to choose, but 4 would be the smallest and easiest whole number to choose. I have 3 test points, and you'll notice that they correspond to what the table has as well. The next section in the table appears to be simply the product of multiple signs. It will be the same as what is produced in my chart. I look at each of the 3 original factors coming from the first derivative of the function. I need to analyze their signs. Are they positive or are they negative in that test point or in that interval? The monomial factor 3 is a constant, and 3 is a positive 3, so it's always positive. That gives me a positive in my first row. Looking at the table, that accounts to the positive that is the first sign in each of the 3 parts. Now I will look at the next sign, which is the x minus 3. For the x minus 3, what possibilities do I have now? X minus 3 is a line. It crosses the y-axis at -3 with slope of 1. When it hits the x-intercept, it will go from below the x-axis, where it is negative, to above the x-axis, where it is positive. That x-intercept occurs at 3. That was its solution. So I predict that this factor x minus 3 will change sign at the vertical line corresponding to its x-intercept, or 0, or solution. If I plug in the test point, a -2 minus 3 is a -5, but the main thing is it's still negative. When I plug in 0 minus 3, I'm still negative. But when I plug in 4 minus 3, I get a positive 1. Note it did change sign at its 0 or solution. This will always occur. These values correspond to the ones now ringed in the teal color in the 3 rows on the book's table. Let's take a look at the last one, x plus 1. When I'm looking at x plus 1, what are the possibilities that I have here? This is a line that crosses the y-axis at 1, has slope of 1, but will hit the x-axis at its 0 or solution, -1. I predict it will change signs here across the vertical line at -1. -2 plus 1 is -1, so it is still negative. 0 plus 1 is 1, so it is now positive. And 4 plus 1 is 5, it is still positive. It did meet my expectation and change sign at its 0, -1. This will always occur for linear factors. This corresponds to the last 3 signs in the product in the table from the book. To get the solution now, what I need to look at is the combination of these signs taken together. Since these were originally multiplied in the first derivative, I need to multiply the signs to know what sign the first derivative has. A negative times a negative is a positive times a positive is positive. 2 positives are still positive times a negative is negative. 3 positives multiplied together is positive. This tells me that it will be increasing or going uphill over the following intervals, from -infinity up to -1, and again from 3 to infinity. It will be decreasing in between the 2 critical points, between -1 and 3. Let's now take a look at the last part. The last part is predicting where I have my relative extrema. If the first derivative is positive, that means it's going uphill. And I can put upward slanting lines in each of those 2 regions. When the first derivative is negative, it is going downhill. If I look at these and I sort of imitate what their graphs would look like, that means it has to be going up, and now it's down, and now it's back up. This clearly means I must have a relative maximum occurring at x equal -1 with the value of f of -1, and I must have a relative minimum at, having trouble writing with my pen again, at, not at x equals 3, occurring at the y value f of 3. This is how we can analyze the first derivative test and use it to produce a picture of the graph. Let's take a look at another example. In this part, we're now going to look and see how to apply what we've learned about the first derivative test to the graph of f of x equal x squared divided by the quantity x squared minus 1. In order to apply the first derivative test, we first need to factor the function completely and think about where its domain is. Anything that is not in the domain of the function cannot serve as a critical point. It is extremely important that you throw these values out before you find the first derivative. It is very easy to forget that if it is not in the domain of the function, it cannot be a critical point. If I were to factor this one, I would find that I would get x squared divided by x minus 1 times x plus 1. This graph has two vertical asymptotes, one at x equal 1 and one at x equal negative 1. I cannot allow either of these values as critical points because the function is not defined there. Now that I know that these are not in the domain, I can find the first derivative of the function. You can either use the quotient rule, or you could rewrite x squared minus 1 as x squared minus 1 to the negative 1 power and use the product rule. It doesn't matter, you'll get the same result in either way. I'm going to apply the quotient rule. First, I find the first derivative. This will give me the denominator, x squared minus 1, times the derivative of the numerator, which is 2x, minus the top, which is x squared, times the derivative of the denominator, which is also 2x, all divided by the denominator squared. We will want to clean up the numerator a little bit, but it is not necessary to multiply out the denominator, and in fact would make our job harder. We want to leave the denominator in its squared form. In the numerator then, I can simplify this, and I will come up with 2x cubed minus 2x minus 2x cubed, all over, again, the denominator squared. The 2x cubes cancel, and this leaves me with negative 2x divided by the quantity x squared minus 1 quantity squared. Now I need to find my critical points. Remember that critical points come from two locations. One, the first derivative is equal to 0. When does the first derivative equal 0? Having more trouble with the stylus. Okay, the first derivative equal to 0 when you have a fraction for the first derivative means that the numerator is 0. That means I have to have negative 2x equal to 0, but the denominator cannot be 0. I already know from analyzing the original function that the denominator of the first derivative will be 0 when I have either x equal 1 or x equal negative 1. But since those values are not in the domain, they will not be able to serve as critical points. The first derivative equal to 0 gives me the solution that x is 0. The second part, which is when the first derivative does not exist, but the function does exist, this is the one that you have to be the most careful of. In this case, students who did not analyze the domain of the function first would want to tell me that 1 and negative 1 are critical points on the graph. They are not critical points. It is true the first derivative does not exist, but the function doesn't exist there either, Therefore, they are not critical values. I only found one critical value. That means that when I look at this, I need to divide it up and analyze it with only one vertical bar in my chart. Let me show you the method that I typically use. When looking at the chart, I'm going to look at the original factored form of the first derivative. When I look at the factored form of the first derivative, I can draw the following boxes around the factors. Factor of negative 2x and the factor of x squared minus 1, which is squared. You could write the x squared minus 1 twice, but since it is raised to a higher power, you can also list it just one time. That gives me a row for the original monomial factor minus 2x and a row for the binomial factor x squared minus 1 quantity squared. Then I need a row for the combination, which gives me the entire first derivative. I draw 3 number lines. I only had one critical value at x equals 0, which I'll put more or less in the center of my picture. Now I need to analyze the signs. This divides the original domain up into various regions. If you want, though it is not required, you can also use the values that split up the domain, the 1 and the negative 1, on this chart as well. We can do it now, and let's just see if it makes any difference. So I'm going to draw dashed lines since we're trying to figure out if those changes in domain are going to make any difference in analyzing the sign of the first derivative. First, we need to find some test points. To the left of negative 1, I would probably use a test point corresponding to negative 2. Write it and circle it so you know it's a test point and not a point on the graph. Between 0 and negative 1, I don't have a great choice, but negative 1/2 is probably the best I can do. Between 0 and 1, I'll use 1/2. And above 1, again, 2 makes a good test point. Notice that the first one is negative 2x, which is a linear function. It crosses the y-axis at 0, which is also its x-intercept. It has slope negative 2. I predict that it will only change sign at its solution of 0. If I plug in a negative 2 for x, a double negative would make that sign be positive. If I plug in a negative 1/2, it's still positive. But if I plug in 1/2, a positive times a negative, that's negative. And negative 2 times 2 is also negative. Note that the domain issues at negative 1 and 1 had absolutely no effect on the sign of that factor. What about the x squared minus 1 quantity squared? For this one, we can actually use a bit of a trick. The trick is to note that the thing is being squared. If it's being squared, there's no way it can ever be negative. That's why I like to leave factors to even powers with the power out, because I know that I can just put a plus straight across. Now to combine the signs for the first derivative. 2 positives divided will give me a positive. Positives give positives, 1 negative gives a negative, and I notice now that adding the negative 1 and the 1 from the restriction to the domain had absolutely no effect on the chart. This is always going to be the case. So from now on, you do not need to add those into your chart. We could simply have had 2 test points, one to the left of the single critical point 0, one to the right. However, when you do that, be sure you don't use the critical point or don't use a test point that corresponds to one of the values that does not exist on the function. In other words, if I had left it without the 1 and the negative 1, I would still want to be sure I did not choose -1 or 1 as a test point because those correspond to places where the function doesn't exist. So for my test point, I would have chosen -2 to the left and 2 to the right. I could have chosen -1/2 and 1/2 as well. What does this mean about the graph? Let's interpret our results. Our results now tell us that what we have discovered is that it is uphill in all of these regions where the first derivative is positive and downhill or decreasing in the regions where it is negative. That means that my graph is increasing over the interval from -infinity up to -1. Notice I had to break where the domain breaks. And again, from -1 all the way to 0. It will be decreasing then from 0 up to 1, where the domain has a vertical asymptote, and then again from 1 to infinity. This means that I must have something occurring at the critical value of 0. Since it is generally going uphill and then changing to coming downhill, this must mean that my graph is doing something like this. This must mean I have a relative maximum occurring at that value. My relative max occurs at 0, and the relative maximum value will be f of 0. So the relative max occurs at the x-coordinate and has value of the y-coordinate. If I look at my original function, if I allow x to be 0, I would get 0 divided by -1, which is 0. That means that my relative maximum is occurring at 0, 0, and my relative max is 0. Let's look at the actual graph and see how we did. Did we get relatively close to what it actually looks like? If you look at the graph here, you'll see that it does meet our expectations. It is increasing from -infinity up to -1. Following along the graph, it's going uphill. It is again increasing from -1 up to 0. It decreases from 0 to 1 and also from 1 out to infinity. And I do have a relative maximum of 0 occurring at x equals 0. Our expectations were spot on. Now let's look at another example and apply the first derivative test again. Let's look at example 2. This is the function x times quantity square root of 3 minus x. First, we analyze the domain. What is the domain of this function? Since we know that we can't put a negative under a radical, that is our first restriction. Our domain, we must have 3 minus x greater than or equal to 0. This implies that x must be less than or equal to 3. Oops, sorry. Having a little trouble getting it to write. This basically means that I can use 3 or smaller values in the radical. So my domain is from -infinity up to 3. I can use 3. That would just give me 0, but 3 times 0 is 0. This does mean that any critical value that appears to be to the right of 3 is not, in fact, a critical point. Now that I've analyzed the domain and I know what values to restrict, I can take a look at the first derivative. Taking the first derivative of the function, I would need to apply the product rule. The product rule would tell me if I take the derivative of x, I get 1, which would simply give me back the radical by itself. Taking the derivative of the radical and multiplying it by the x, I get the derivative of a radical is 1 over 2, the square root of the radical itself, then times the derivative of the inside function. The derivative of 3 minus x is a negative 1 for the coefficient of negative x. If I write this out, this would give me the square root of 3 minus x over 2 times the square root of 3 minus x. Now clearly, if I allow the denominator of the second one to be 0, that derivative would be undefined. That would be for the value of 3. Let's take a look at a better way to analyze where the critical points are. In a case like this, where I have two separate terms and radicals involved, it is often easier to rewrite the two terms as one fraction by getting a common denominator. To do that, that means I need to multiply the one on the left by a 2 and the square root divided by itself. Anything divided by itself is the number 1. That would lead me to have 2 times 2 of the square roots, which means I have the square root squared, which of course will lift off the radical, all over 2 times the square root, and in the numerator, I will also have a minus x from the second one. To simplify a little bit further, this would give me 2 times the quantity 3 minus x, since the radical was squared, and I will have another minus x, all divided by 2 times the square root of 3 minus x. Simplifying the numerator a little bit more, I can get 6 minus 2x minus x over the common denominator, which would finally lead me to 6 minus 3x divided by 2 the square root of 3 minus x. When possible, it's usually easier to simplify the first derivative and then look for critical points. Now let's find our critical points. Looking at this particular version of the first derivative, I need to know two places. I need to know when is the first derivative equal to 0, and secondly, where is the first derivative not existing but the function does. Having a little trouble with the stylus. Okay, now let's analyze the first case. When is the first derivative going to be 0? This will occur when the numerator is 0, but the denominator is not. If I set the numerator equal to 0 and solve, I get 6 equals 3x, or x equals 2. When x equals 2, the denominator is not 0, so x equals 2 is definitely one critical point. When would the derivative not exist, but the function does exist? Remember that the domain of the function is negative infinity up to 3 and includes 3. Looking at the first derivative, to find where it does not exist, I need to find out where either the denominator is 0 or I get negatives under the radical. I'll get negatives under the radical when I'm to the right of 3, but those values are not in the domain, so they cannot be critical values. However, I know that the denominator would be 0 if x were 3, and 3 is in the domain, which means it won't be allowed in the first derivative, but it is allowed in the function. That makes 3 a critical point. This gives me two critical points at 2 and at 3. Now I'm going to take the most factored form and I'm going to split it up according to my factors. Looking now at the factored form, let me outline them in a different color. 2 is a factor by itself. The radical is also a factor. and the 6 minus 3x could be considered a factor, or you could factor the 3 out of it and have 2 more factors. It's up to you. Let's write these out to the side. I'm going to leave 6 minus 3x as one factor. 2 becomes a factor by itself, and the radical of 3 minus x is also a factor. Together, these all produce the first derivative. Let's draw a number line for each of the factors and one for the first derivative. When I put these onto my chart, notice that I need to divide up these number lines according to the region separated by the critical value at 2 and the one at 3. 2 on the number line is to the left of 3. You do not need to make these to scale. You want to leave enough space to easily have room to write down the signs without being cramped. Now let's find some test points for each of those regions. What is a good number that is to the left of 2 and is in the domain of the function? Remember that the domain of the function, which I'll rewrite again up here just to make sure you remember, is from negative infinity to 3 and closed. I'm going to use the value of 1 or 0. Either of those is a good choice. 0 is usually easier. What about between 2 and 3? That's not a great spot and not a great choice, but I'm going to use 2.5 or 5 halves. What about above 3? Again, think about the domain. The domain cuts off at 3. I shouldn't be looking up here at all. If the function isn't defined there, there's no point looking for the sign of the derivative there. Now this gives me only 2 regions, to the left of 2 and between 2 and 3. I'm going to use my test point and plug in values to see what I get. If I plug in 0 to 6 minus 3x, I get 6, which is positive. 2.5 times 3, well, that means I'm doubling it and taking half of it again, or multiplying it by 5 halves. When I do that, I get something that is bigger than 6, and it's negative, so this becomes negative. 2 is a monomial factor, which is a constant. It's a positive 2, so it will never change sign. The radical is misleading. Radicals, as written, have to have some kind of sign out front. That sign out front determines the sign of the radical if it is an even radical, and it can never change. So in fact, it doesn't matter what I plug into that square root. Square roots without any sign out front must always be positive. Combining the 3 signs together in each of these, I get that the first derivative is positive between negative infinity up to 2, and it is negative between 2 and 3. That means it is increasing from negative infinity to 2, and it is decreasing between 2 and 3. If I draw what it looks like, this means that it was going uphill and now it's coming downhill, which must mean that I had a graph that did something like this, which must mean that I have a relative maximum occurring at x equal 2 with value of f of 2. Let's look at the actual graph to see how close we were in finding where the relative extrema are. Looking at the graph over here on the left, you can see that we did extremely well. Here at 2, you'll see that the graph not only has a relative max, but it is in fact the absolute max of the function. You can also see that there is no other point. It is increasing from negative infinity up to 2, and decreases from 2 to 3, where the graph abruptly stops. This completes the video on the first derivative test.